Okay. Hi guys. My name is Sai. Like the super cool Greek letter. And you can spell it like this. If you want to use, letters. And I am on a journey to try and get everybody to not hate math a little bit. I just want everyone to hate math a little bit less. So, possibly love it. So today we are going to talk about, we got some more board space. We're going to talk about vocabulary or definitions, which I think is the most important thing in any topic. But first topic is going to be linear equations. And we're going to reference ideas from proportional relationships. And so we will end up defining both of these, but we're going to start with some other terms. Just because, I think it'll be easier later if we kind of connect things to what we know already. That's how I do it, at least. I don't think you can learn something unless you can connect it back to something you already know. So we're going to start with triangles. Most people know about triangles, I think. And we're going to start by classifying triangles by angles. And so angle is kind of, it's the measure. Usually we use this as our baseline. If you start at like maybe, if it's your x-axis, if we start connecting ideas, and here's your y-axis, I guess, this is what we're measuring. So if you wanted to put it onto a graph, a Cartesian graph, which is what we usually know, which is like a x, y, it's a letters. We're using letters, x and y's. And z's, sometimes use z's. I guess other things also have letters, but these ones we know. So there's 3 main categories of angles. So we like to classify them based on 90 degrees. This guy is kind of like our anchor. And if we have a 90-degree angle, this is a right angle. And right angles are kind of interesting because when we draw, I had something I wanted to use to help me draw, but whatever. They kind of look like this. This is our, I don't need to put arrows. Yeah, we're gonna use line segments right now. So this is our right angle. And right angles are kind of interesting because this is why I think we use it as like the anchor point. Because if I am moving in one of these directions, it has absolutely nothing to do with the other direction. So like if I am going up, you can go up without moving side to side at all. And you can move side to side without going up at all. So, it'll make sense later in math, but that's an important thing. The fact that you can separate the directions. It's kind of cool, I think. So let's redraw this so it doesn't look insane. So we have right angles, which are exactly 90 degrees. And then we have acute angles. The tiny little acute. That's how I remember it. And this is going to be anything that is less than 90 degrees. And so just to review also, we're going to be using less than symbols, equal to symbols, and greater than symbols. Let me circle them. It doesn't look so crazy. It all looks crazy, but that's what these are. So we'll say less, because we read from left to right, so it is smaller than other side, and then this is greater. Yeah, don't judge me. I can't spell. I don't know don't worry about that. Yeah, I'll put it down here. It's gonna be greater than 90 degrees. Looks something like that. So yeah, what we are going to talk about specifically right now, though, is right triangles, because we are going to be talking about linear equations. And you might not know a lot about linear equations, and that's fine. But some people, you might know that there's, we usually use x and y. So we have two different directions that, they're connected to each other. They're buddies and everything, but we want to talk about them as two kind of separate things. We want to map x against y. So that's why this right angle separating two angles in completely, different ways. We want to compare to there. We want to see if we're, how we're moving from x to y. So it'll make a little more sense later. So now we see what a right angle is. Let us talk about a right triangle. I don't know. This is my cat. You might be able to see her. Her name is Yoshi. She's a lovely little girl. She's hungry, so I have to do this kind of quick. So yeah, right triangles. We can kind of piece our words together. So right just means that we have a right angle going on, and then triangle, just traditional triangle, three sides. So that's kind of cool. This is also important. We got three sides to a triangle. Everyone knows, well, no, not everyone knows that. Let's not, we want to make math more comfortable. So in case you didn't know, three sides to a triangle. And so what we're going to talk about with a right triangle, kind of cool, we're going to start, apologize to my sister, I'm going to use her book. But we're going to start with a right angle, and we're going to make the right angle a little different. I think it'll make sense. Yeah, it's going to make more sense. So we're going to do it like this, because I can. So, Jesus. Oops, sorry. Maybe I shouldn't say that. Cut that out. Okay, sorry. So here we go. We got two different sides. But first we have a right angle. So I've just made a right angle. And I used a book because most corners in books and stuff are right angles. Just because, also another reason why right angles are cool. It means that you can increase how wide your book is or how tall your book is, and it has nothing to do with the other side. Because imagine if you made a triangle book, that's kind of hard. Imagine if you had maybe, or I feel like a better representation, maybe a trapezoid book where they're not completely different. We got different angles and it's still a quadrilateral, four sides. Eventually you can't make this side as long as you want, because eventually they're going to cross into each other and it's going to be a triangle and you've completely changed the shape. But if we have this, you can make this as long as you want and this as long as you want, and it doesn't affect the shapes. At least of the book. So yeah, another interesting reason why that's kind of a standard thing. And you could just pick up a book to do it. But, so here we go. We have our right angle. So I'm going to label this. And then what makes up our right angle, the two sides of the triangle. So sides of triangle that make our right angle. We have two of them, and it's always going to be two because you need two lines to make an angle. So two sides of the triangle that make this right angle, these are going to be called legs. So that means that right here and right here, these are the legs of the triangle. And so we know triangles have 3 sides. We have 2 of them already. And then 3 minus 2 leaves 1. I like to convince myself. I still know how to solve problems. So when we connect these, because that's how we make our triangle, they gotta be connected, or else it's not a closed figure. Okay, something like this. Let's get rid of these middle bits. And so we have one side that is going to be opposite the right angle. And this side, or one side in triangle opposite the right angle. And we're gonna call this, cool word, sounds kind of scary, but it's not that scary. Once you start working with it, it can be a little bit scary originally. I will most assuredly admit that. But it's called the hypotenuse. So that is what this is. This side that is opposite. You could sit anywhere kind of on this hypotenuse. That's what opposite means. And you're always going to be looking at this angle. So his viewpoint angle. So always opposite that. That's what that means. And so, yeah, we'll work with those later. That's kind of our first part. We're going to use it to explain slope. So we'll see. If that word comes up, maybe start thinking about how they might connect. It's a good way to learn, is to try and connect ideas together. So we're going to start now. A little crazy, kind of a jump. Actually, no. Yeah. I want to start with we're going to start with a linear relationship, because I think it's the most broad thing. And also, I have a sheet that I'm going to try and create as a PDF and upload underneath this video. So, just so you guys can follow along if you want to, or keep it as your notes, whatever you want to do. And so, here we're going to talk about what a linear relationship is. And so, she's really upset with me. Okay, give me 1 second. Okay, so I just fed her, so it should be a lot more quiet. So we're going to talk about a linear relationship. And I think it's the most broad of, at least, linear equation, linear relationship, and proportional relationship. We're going to, Am I going to do that? Yeah, we're going to do that. Okay, sorry. We're going to do that. So linear relationship is, so if we have a relationship, just kind of like in real life, you got a relationship between two, usually we're going to talk about kind of the most basic relationship. So I guess you could say that. You could have relationships between a bunch of people, you could call them families, you could have relationships between, 2, 3, 4 people, you could have, I like to think about it when people have relationships between money and something else, but that's kind of boring. Relationships, we usually talk about 2 different people. So, here we go. We'll have maybe our X and we'll have our Y. And so we have a relationship between 2 different variables. It could be like two different people. But the thing is the way we see it is usually X is going to be like your independent. So if you're actually assigning it to real things, it's going to be like, I guess, things that are pretty consistent. So you could do like quantities. like that, how you count things is not really going to change. Time, how we count time doesn't change. How you count amounts of things, something that's not really going to fluctuate that much. Like days, how you count days, that kind of stuff. And then we have our dependent. This guy is the one, it's kind of the interesting thing. It's like, given this, how we usually count something, what the heck's going on? So, yeah, you could, maybe not as much as people, but like if you think about like prices are usually pretty consistent, how you have a quantity. No. Yeah, that's the thing. Sorry. Scratch. Prices are not consistent. You know, you could buy 2 of something and it's completely different than the price of 2 of another thing. So that's where, funky business happens. If you're counting things, it's pretty objective. It's not like, no, that's not really 2 pencils to me. Like, this is going to be 2 markers. It's always going to be 2 markers. But if you want to talk about the price of the markers, that depends on a lot of things. It might depend on, what type of currency you're using, what time of the day, how expensive the materials are, if it's what season it is. These are all important things. But how many markers never changes. I want 2 markers. Okay. But what that means in our world, that's going to change. So that's kind of this thing. And so we are talking about relationships where if we graph them on this XY axis as 2 kind of different directions, independent, they make a line. So that's what a linear relationship means. It could be a line like this. It could be, we could have another line over here. Sorry, it's a terrible arrow. That's going down. We could have that goes to the origin. This guy doesn't go through the origin. The origin is where the lines meet, X and Y axis. It's where they're both 0. Kind of cool. So that's what a linear relationship is, at least visually. And so, what if you wanted to, I'll also put a linear relationship like this. How would you know what to graph? So, usually it might show up like this, where you have like, and this is how you can also know that you have X is a independent variable, because you could put whatever numbers you want for X. Like we could just go 1, 2, 3, 4, 5. They're usually consecutive. That's how we would count something. And then, and then Y will have some corresponding thing. So it might be easier later once we talk about what the formulas look like, but in a linear relationship, if we go up by 1 on the X side, that means we'll go up by whatever this changing increment is, but it's going to be the same. So for every 1 we go up here, we change the same amount. So, say we start with 3, and I wanted to make this next one 7. We changed, this is a +4. So that means if you wanted it to be linear, we have to keep doing +4. So go up 1, well, +4, it's 11. +4, 15. +4, 19. So kind of looks like that. Also, if I ever make mistakes, please point them out. In anything, in small math, in arithmetic, in concept, in theory, not spelling though. Don't point those ones out. I don't care about that. But say we wanted to, make a rule. That only gave us, sorry, let me redraw that. So this only gives us, what 4 points are. So we have 1 point, 2 points, 3 points, 4 points. If we wanted to actually graph these, and the points would look like we do our points as X, Y. So here we would have 1, 3, 2, 7, 3, 11, and 4, 15. And you can check these. It will make a line if you don't believe me, but I think it will. Pretty confident in that. And so, maybe we wanted to represent what any of these x's were to any, to get any y. We could look at, I want to know what 70 is, or I want to know what negative 100 is. I'm not going to sit here and do +4 the entire way. So we're going to figure out a rule. And that rule, in general, I would call the linear equation. So we have some linear relationship. We know it makes a line. We know the change is consistent every time we're going up. So now we want to talk about a linear equation. And it's kind of hard. There's a lot of different ways to write linear equations. There's 3 forms you're going to see a lot of the time. And I'll just write their names up here. We'll talk about them in a second. So we have slope-intercept is usually the most common, I'd say. Yeah, at least that I've seen. Second most common is our standard form, which is kind of funny that standard form is second common, or second most common. And then our third one is going to be point slope. And so that's kind of, this is kind of interesting. I do have to do a little more investigation into standard form and what exactly these coefficients, we'll do a little investigation on that, maybe on Desmos. But this kind of tells us that in order to graph a line or to make a line equation, slope is really important. Slope is arguably crucial. But kind of the ways we can make a linear equation is if we have the slope and the intercept, the slope and a point, or you can also do a point and a point. So that's enough information to give you the equation. And then this is an interesting one. You can do a point and then a relationship to another line. And usually these relationships, we will say it is parallel or it is perpendicular. But usually, or not usually, this kind of falls under point slope, because if 2 lines are parallel, that gives you a clue about their slopes. Parallel means that they have the same slope. You might not be able to see that. So here, parallel lines is same slope. And then perpendicular lines, which we can talk about what that means also, usually means we have opposite reciprocal. Which we can also, we'll talk about that in a second too. That's kind of a later situation. But yeah, so those are maybe I should cut. We'll see. We'll see. Those are the different types of line equations you might see. Or yeah, and so a linear equation. What's kind of a definition of this is we have an equation. It might be kind of intuitive, where every variable and for this case, we're going to have 2 variables. We're going to have x and y. Well, you can have x and or y. It doesn't have to be both. And I'll show you that in a second. every variable has an exponent of 1. So, yeah. Let's see what different line equations can look like. What is that? What might these things be? We can have, let's see, something that looks kind of simple. Y equals 1. We have an equation. So I guess that's where we go. Equation, and then variables have exponent 1. We can use these as our 2 checks. So we got an equation going on, and then y is also equal to y to the first power. So we'd have an exponent of 1. So there we go. All variables exponent 1. We got an equation going on. And this would look like, we go and we have our y-axis. We're going to go to where y is equal to 1. And then every single point on the x-axis is going to be 1. So we're going to get a horizontal line, at y equals 1. And so another example could be, shorten that up a little, x equals -4. So here again we have an equation. So first check is good. And every variable, we have one variable, x, and we could write this as x to the first exponent of 1. So there we go, a line equation. And what does this look like? It's important to visualize, I think. And it might take a little while. Like, I've been doing this for a minute, so if it takes you like 5 or 10 minutes just to draw out what a graph might look like, that's completely fine. We're just trying to kind of gather intuition. And it happens slowly. So if we have -1, -2, -3, -4, then that means that no matter where we are, x is going to be -4, no matter what y is. So there we go. We have a line. And this is not necessarily a function, but it is a line. So if you have more questions about that, we can talk about that in a different video. But let's look at what another line could look like. Say we have something that looks like x plus y. So now we got 2 variables. And so x plus y equals 2. So we have 2 variables. Don't let that scare you. It's kind of a similar process. We have an equation, and then each variable, so we have x and y, are both to the first power. And what would this look like? I'm just going to go through these pretty quickly. And we can talk about why they look like this later. But this is going to go through 2, and then, something like that. So, not too shabby. We got a straight line. It's a little slanted. That's okay. We can have slanted lines. They're still straight. And it does not go through the origin. So, that's kind of interesting. And then, let's see, I guess we'll do one more. So -2x plus y equals 0. This is going to be another straight line, but it's going to be positive and through the origin. Kind of a little bit steep, a little steeper than just straight through. So yeah, that's what a linear equation is. That's our linear equation. We'll talk about, I guess just real quick, what standard form looks like. So we have ax plus by equals c. So we want both variables, whatever variables we're talking about, to be on our left-hand side. And they're allowed to have coefficients. That's cool. We can do that. And then we want numbers on the right-hand side. Some people, they really like a to be positive. So, just try and make a positive if you can, and then let b and c be whatever. But usually when they define it, they'll mark it. Sorry. It's kind of like that. So yeah, you'll see how it goes. But that's usually how it is. So yeah, we talked about some good things. Now back to kind of relationships a little bit. Actually, no, we're not going to talk about relationships. We're going to go back to these triangles. What's up with these stinking triangles? Why are we talking about them? So, let's go back to our handy-dandy Doctor Who book, because we love that. It's my sister's book. Don't ask me about Doctor Who. Sweet angel. Here we go. We have a right angle, and I'm lining up this right angle with kind of up and down and side to side, just because that's how I'm going to do it. So I'm going to do it because I can. And we're going to think about a situation where we are going from one point to another point, and we are taking the most direct route, like the shortest route possible, which is going to be, this straight line between. If you don't believe me, think about it for a little bit. That's another cool thing we can talk about. So, I'm sitting here. Here's my first point, and here is point 2. And so, the straight, the most direct way, it's kind of hard to describe that. I don't know what to do about that. It's kind of, maybe you could use a compass if you wanted to. And we have north, south, west, east. It's kind of like northeast a bit. It's kind of good direction to explain how to get there. But it's kind of hard. And especially if someone doesn't know about the compass. So you could do like kind of halfway between, maybe X and Y. You could do, some people like to use time. What do we call this? Maybe like 2 o'clock. Like 2 o'clock, That could be a direction, but it's a little tricky. So standardly, we are going to break this direction into how far up and then how far to the side. Yeah. And so we call how far up we went. This is our rise, so how much we've gone up. And then how far right or left in this X direction is going to be our run. So, if you're running across the field, how far did you go? It's kind of not too bad. So yeah, we can have, I guess, didn't really need much more formal directions. So I guess our rise is equal to the change in y, which is kind of cool. That's what this means. It's a delta. It means change. And then run is equal to the change in x. So we went from here to here in the x direction. We went from here and here to the y direction. And so then how do we use that to describe this direction? So we are going to call this direction the slope. And the slope is going to be kind of described as the rise over the run. Or we can say change in y over change in x. And initially, I think it's kind of hard to remember that it's rise over run. A lot of people will just be like, rise over run, just remember that. But I guess kind of in, maybe an easier not anecdote, but we can, my poor cat, she's so sad. we can try and make it a little more intuitive. Imagine this is you, and you're sitting down on the ground, and you've got, you got a friend who lives in an apartment building. And we'll say 3 doors. I like my example. And so this is where your friend lives. The kind of interesting part is, we might think about run over our eyes because, usually that's what we can see. That's the realm we're on, is what's in front of us. But we have to get to where we have to go and then analyze, because little old me can't just grow some wings and flap on up here. It's not how that works. I have to climb these stairs. That's what we got to do. We got to climb the stairs to the different floors. And so that means that I have to go up first. Yeah, little me, got to go up first. Sorry, I'm getting lost in my own example. We gotta go up, and then we can go over in order to get there. And I think that's mostly just human convention. Well, I guess not all the way. We care about our line, the way we've set it up. If this is our number of silly books that doesn't change, I care about how this is changing in respect to this one. This one's not that important, but I told you how much I wanted to move. I told you how many books I wanted. The price is what's interesting. So, yeah. That's how you can kind of think about it that way. And so the slope is going to be how steep our line is. And so we can have positive slope, negative slope. Your slope can be steep, it can be shallow. So let's see, what does that look like exactly? Well, no, we could talk about it in just 2, I think. Okay, so we're going to a positive slope. Is we usually read things from right to left. So we're not going to change that in math, because why make things even harder? So if right to left, you're going up, that's a positive. So even if it's not a lot, just a tiny little bit, we are going up when we're going right to left. So that means we have a positive, shallow slope, because we're not going up a lot. Kind of for each point, imagine try and have equidistant points. We're not, you're climbing very little for how much you're going out. Like if this was a hill and you were running up a hill, that's not that bad. But here we might have a sharp decline. This would be a kind of a hard hill to go down. So we're going negative, or this is negative, because if we read from right to left, from here to here, we've gone down. For every over to the right we go. And I'd say this is relatively steep, because, you drop a ball down that, it's going to go real quick. I'd call it steep. I wouldn't snowboard down that as a beginner. So, yeah, those are those things. Now, I guess one more thing. We're actually going to talk about a y-intercept. So y-intercept has to do with, it might make sense, the y-axis. And so our y-intercept is where we are intercepting. So when you go through, when our line passes the y-axis. And so how do you describe that? Y-intercept, it's a point. So, in this case, we are going to pass, we have a line, we're going to pass out 1 point usually. So it's whenever they touch each other. And you will describe it as where that is on the y-axis. So maybe we go down, and this is like negative 4.5. Sorry. And that's what you would say. You'd say that's what the y-intercept is. Usually for letters, we call y-intercept b. And I'll go back for slope, we use m. It's just kind of standard convention. Not too crazy. So yeah, that's how we use that. So this is what our y-intercept is. And so now we're gonna go kind of back to these relationships, because we know about equations. We kind of get that, but we're gonna talk about a more specific line or linear relationship, and that is a proportional relationship. Yeah, and so proportional relationships, I'm trying to think. Yeah, proportional relationships, they're not terrible, but proportional relationships are always going to be a line. They're going to look like, lines that go through the origin. And we can talk about that in a second as to why. But it's going to be a straight line that goes through the origin. It could also be a negative straight line that goes through the origin. The steepness doesn't really matter. But we describe it as the ratio between the output and input, or we could say y and x is equal at all points except 0, 0. Yeah, and that's because 0, 0 is kind of a hard relationship. It's kind of weird, because if you had 0 to 0, you could multiply 2, you can multiply 4, you can multiply anything you want to. You don't really know what all made up this 0, you just know one part of it is 0, so that's why we don't really talk about 0 sometimes. And then another reason is this ratio we're talking about. So ratios, quick recap. We have y to x, or you could represent it as a fraction. But either way, we're going to represent it as a fraction in this case. We know that this ratio, y over x, is going to be equal to the same thing, no matter what point it is. I'm not talking about here, but no matter what point. And we're going to call that number it's equal to m. Eventually that is going to be the slope. We can talk about why it is the slope. It kind of, well, not kind of, it might make a little bit of sense. Yeah, it might make a little bit of sense, just because if we talk about y over x, that's kind of a rise over run kind of thing. So that's our slope here. It's interesting. So yeah, that's what proportional relationships will look like, at least in an equation. So that's how we put it in an equation. When we look at it in a graph, so it's going to be a straight line going through the origin, and this guy's going to have a slope of m. And then if we look at it in a table, we always have 0, 0 is going to be a point. So that's how you can tell if it's proportional. We know it goes through the origin. And then other than that, we have to know that this will be the same. So yeah, we could just go maybe -1, 1. We'll just use 3 points right now. So if we are increasing by 1, that means we're going to increase by m on this part. And you can kind of maybe see it like that. So if I go up by 1, I'll go up by m. And if I go down by 1, that means I'm also going to go down by m. So it's going to look something like that. And so once we kind of branch off of this, now we'll start with y over x equals m. So this is our equation for a proportional relationship. Sorry if it's hard to read. So equation for the proportional relationship is y over x equals m. And so, you know, I don't like fractions all the time. Some people like fractions, and that's cool. It's cool for them. But we are going to talk about this without the fraction. So how do we get rid of fractions? Or not get rid of fractions, but you multiply what you're dividing by. Because if you don't want to divide, just multiply by it. Just multiply by it. Because why not? So we have x times y over x. So I don't want to divide, so I'm going to multiply. And then we can cancel that out. But they're equal, so that means I also have to multiply by x on the other side. So this gives us y equals mx, which is kind of cool, just saying, because now this is still our equation for a proportional relationship, but now it is in this weird thing we call slope-intercept form. So here's our slope, and then we'll talk about the intercept in a second. The intercept is involved here. It's a plus 0, because you can add 0 to anything. It's not really going to change much. So our intercept is 0, so we can think about this plus 0 here. And so we have our slope plus our intercept if it is 0. So that means we have a straight line, so any line that goes through the origin. So that's kind of cool. Kind of cool as a proportional relationship. I think so, at least. And so, yeah, here we go. This represents, let's say one more time, straight line through the origin. But what if we want to move it up a little bit? What if you want to go up or down or anything? If we're going up a tiny bit, usually the easiest point to see it is the origin. We want to go up. That means that we're going to change we're going to change the y-intercept. And effectively, it's going to go up a little bit at every single point. Because we can't just have, like, you know, that's not a straight line. So in order to change this y-intercept, we have to keep the line the same. We're just moving it up a bit. And so that means every single point, you know, this is one rule that works for all points, which means that y1 is equal to m times x1, y2 is equal to m times x2, any single point you wanted to use ever in the world. So if every point is moving up by this amount b, that means that's where our y-intercept comes into play. If it originally was 0, we're moving every single point up a tiny bit, because that's straight line, moving it up. This is what we call our slope-intercept form for a line, y equals mx plus b. Because here we have our slope, and here we have our y-intercept. And anything like that, here we go. We could draw it a little bit differently. Here's B though. And then this is This is our line. This is our line. Y equals mx plus b. And our slope is m. In this case, it's going to be negative. So m is going to be some negative number. We don't need to know what it is right now, but just to think about it. So yeah, that's our vocabulary. I'm happy. I hope you guys stayed along for as much of this as possible. But yeah, I just want everyone to know you guys are great mathematicians. I don't care what level you're at. Math is for everybody. And math's important, even beyond just putting it on numbers. You know, what you did today is you broke down problems and we thought about things like how can we make rules for what relationships are. You know, you could arguably, some people think this is the fun part. They're always like, oh, why do I care about this? You know, so we could talk about real world. We could talk about, you know, people almost as a concept. So here we go. If you, let's talk about it like this. So in kind of time, or maybe this is our perspective, we want to talk about when we intersected with our friend we call Y. If we want to talk about when we intersected it, was it at a good time in their life? Was it at a good time in our life? Yeah, sorry, just kidding. I'm going to cut this a little bit. But we want to talk about this with respect to this. So, you know, maybe I want to talk about my life when so-and-so cut in. So here's my life when some friend came into the picture. I want to talk about where was I, you know? Was I at a good point? Was I at a bad point? So we could talk about maybe healed, comfy, in self, all that kind of stuff. And if you want to talk about a bad thing, maybe we're feeling really insecure and scared. So maybe I met this friend at a hard time, a really hard time. And, you know, we can think about as time has gone on, this kind of very progressive thing, as time goes, what happens? Did this person, with the time, did they ruin my experience? So in 1 hour, I give friend 1 hour, have they improved or decreased? And so we'll say they improved it. So we'll give it a positive M. So we started at a negative place, but they're helping us. So that's how you can kind of gauge trajectories almost. Like if I continue to keep so-and-so in my life, where am I going to get to? Or you could talk about a habit maybe. Like maybe this is your productivity and this is how much time, you know, you spend reading. Like maybe you were really, really bad. Like you used to burn books. Or you could just talk about your comfortability of life. Like you are really sad and now this is just adding to it. And we can add more and more variables as you go, but it's just ways you can think about things. You know, obviously you're not going to map out every friendship, but you can think, oh, I continue to feel kind of bad every time I see this person. I'm feeling kind of worse. Maybe this isn't how I would like to conduct my life or spend my energy. But, you know, we can talk about other applications, but that's just one. But have a great day. Do well. Believe in yourself, and don't let people discourage you. You're important, and what you think is important. So bye.